Okay, everybody, welcome back to the podcast, Philosophy for the People. We are joined by a new guest today, Dr. Luke Barnes, author of this very fine book, A Fortunate Universe. Dr. Barnes, it's your first time on the show, so I want to thank you for being here, and I look forward to our conversation today.
Yeah, thanks for having me.
So, you're an expert in this whole fine-tuning argument. It's a fascinating argument. It's an argument that I find myself sort of peeking into quite frequently. I've always found it intriguing for various reasons, and your work has been very insightful and fruitful to read on this subject matter. So we're going to explore that argument today, and we'll see how deep we want to get with it. But before we do, since it is your first time on the show, if you wouldn't mind, a little bit about yourself, your background, how you got interested in natural theology, especially the intersections between philosophy and your background, which is physics.
Yeah, I'm a physicist and astrophysicist. I'm Australian, so I grew up in New South Wales, Australia. Got interested in physics basically in high school. When you can do the maths, the physics is just a whole lot of fun. So I did that at university, and then within physics, got particularly interested in cosmology, so the expansion of the universe and all of that wonderful stuff, thanks to an excellent book called Cosmology, The Science of the Universe by Edward Harrison. That sort of really sucked me in. So I did a PhD in astrophysics and cosmology at Cambridge. But during my time there, I'd sort of heard, as a Christian, just reading a bit of everything and apologetics along the way, and I'd heard about this thing called the anthropic principle, fine-tuning of the universe, so started to look into it and realized that actually there's a whole bunch of scientific sort of professional publications on this that hadn't been covered as much in the popular level literature that I was reading. And so I started to look into it, being able to read it as I was, becoming an astronomer myself, astrophysicist, and eventually realized that the sort of a good review article of all this stuff hadn't been written for a while. So I started writing one myself. So that was published in 2012. In the meantime, I'd moved back to Australia from overseas, and a colleague of mine who had been my honours supervisor and now colleague of mine, Geraint Lewis, was looking for a book to read, and I gave a talk about fine-tuning, and sort of these came together, and we decided to write the book that's behind me that you just showed, A Fortunate Universe. And so that was basically how I got to read everything in this field and then start contributing to it myself. So I have a couple of published papers in various aspects of fine-tuning. It drags you into a whole bunch of different areas.
Right.
So I've read a bunch of stuff in philosophy. I've published papers in philosophy journals on probability in physics, and stuff in physics journals about the nuclear reactions in stars and what if they were different, and what if galaxies formed in a different universe, all this sort of wonderful stuff.
Yeah, well, they often say to ask one question, at least in philosophy, is to ask all the questions, at least eventually.
Yeah,
so
it all connects up. Yeah,
right. Yeah. So it ain't no quick way to tie it all together. So Luke, I want to start with I guess two questions. One is just to ask you my hair's all trying to get my beard straight too.
That way. There. Right. Sorry, I just woke up. There we go. Good.
No, look great.
It's never going to be great, but just that one bit.
Okay. Good enough for government work, right? Okay, so two things. One, I'd like you, just for people who are totally unfamiliar, I'd like you just to give your current favorite presentation elevator pitch of the fine-tuning argument. What is it? What are we trying? What are we up to with this? And then two is, where do you see the fine-tuning argument debate? Where is it today? Right? Where is it today? What's the state of affairs, if you will, if you're going to give your kind of current evaluation of it? So yeah, one then two, if you don't mind.
So the elevator pitch is that I like to think of it as, we see a world around us. There's literally a parrot just outside my window there at my bird feeder. So we see amazing stuff in the world around us. And it naturally, I think for most people, I think why belief in God comes so naturally to most of humanity, for most of human history, of some sort of God, is that it looks like someone's put some sort of thought into this place. Right, all the bits, there's things that just fly, and eat my birdseed, and
Mhm.
are brightly colored, and just the more we look into the interconnectedness of nature, the more that we realize how much we rely on all these things, and the more sort of amazing, machines at that level, and ecosystems at that level, and interconnectedness. And what fine tuning is about is, well, what happens to that intuition as you go looking deeper and deeper down into the laws of nature. So, parrots are biology, but they're made of, various bits and pieces down to cells. And you look inside cells and you find molecules, and molecules are made of atoms. Atoms are made of protons and neutrons and electrons. Protons and neutrons are made of quarks.
Mhm.
Quarks might be made of something, but we don't know. And the question is, what happens to that picture of the world where this place looks pretty amazingly well put together, at least at some level? What happens to it? And fine tuning says, well, look, here's a way we could try and answer that question. What if those fundamental bits of the universe had been different? What if electrons had been a bit heavier, or the force that holds protons to neutrons? What if that was a bit different? Or the force of gravity, or electromagnetism, or all these other things. So there's numbers there in our equations, and it's there's an interesting passage in The Blind Watchmaker by Richard Dawkins, which is behind me somewhere, where he says, basically one of the reasons why we think that there's something to explain, at least in the way nature is put together, is if you took a typical animal and just mixed up all its cells and threw its cells together at random, you wouldn't make something that flies.
Mhm.
And so the question is, if I just took the cells, the fundamental bits of the universe, and just mixed them up at random, throw the constants of nature in a blender,
Mhm.
what sort of universe comes out? And fine tuning says, oh, a dead one.
Mhm.
Well, one that was never alive. Well, you just can't make the sort of complexity that life relies on very general ground. Stuff doesn't stick to itself at all. And so that's my it's probably a bit too long for an elevator pitch, but that's
No, that's
roughly
good.
that's fine tuning. The debate today, actually, I'm about to find out. In about a month, I'll be in at Rutgers University in New
Okay.
Jersey, where there's a summer school in philosophy of religion, where a bunch of people for and against this argument, we've got a bunch of students for a couple of weeks,
Oh,
and they
cool.
are just going to get fine tuning oozing out their ears. And I think there's a couple of places where there's a lot of debate. It does stir up debate very easily.
Yes, it does.
What's one of the things we like about it? In terms of fine tuning, there isn't that much in the physics literature that challenges that fundamental premise.
Right.
There have been refinements of various arguments. Some arguments have dropped out. Some have gotten stronger. Stars were a bit more robust than we gave them credit for. Some great work by an astronomer called Fred Adams on that. Important stuff. But generally, that's, pick a universe at random, and it's probably not going to do much interesting. In the
Sure.
physics literature, is still fairly solid. So the
So
question
the
is,
general scientific data is pretty secure on this, is what you're saying, right?
certainly within the scientific literature,
Mhm.
within the physics literature, you sometimes hear physicists slagging it off. Generally, that's done on, not that, on podcasts and in interviews.
Sure.
And if they want to go and write a paper, be my guest, but it's not happening in physics journals. And so that's in terms of that basic, what if I change these numbers, you would get a universe that doesn't support the sort of complexity that any form of life we can conceive would need. That's fairly secure. So the question then is, what do we do about this fact? And then, everything blows up. So
Right.
my co-author is an atheist, so we agree about almost all of the science.
Yeah.
He thinks that the multiverse is probably the answer to this. That
Sure.
we sort of won the cosmic lottery, but there's lots of other tickets out there.
Amazing.
Yeah, there's a bunch of objections that people bring up.
Well, that's great, right? And I'm not a scientist. I don't pretend to be one usually on the podcast. So when it comes to the scientific data, I say, well, it seems like there's a pretty strong consensus on the points that you just said. So I'm happy to go with that. And then I guess the interesting objections tend to be a little bit wider, a little bit more philosophical, right? So there's three I want to pick your brain on, Luke, and these are the three that just sort of interest me the most. They seem to I don't know, be the most serious challenges. Maybe people have different ones, maybe you have different ones, but I want to get your thoughts on three today at least. One is you brought it up, the multiverse. We got to talk about that, right?
Yeah.
The other is the normalization problem. We'll talk about that. That's an interesting one. And part of that reason it interests me is was presented by some friends of mine, the McGrews, at one point. And had a little back and forth with Lydia on this. And then the third one is the necessity objection. That's an interesting one too. So we can take them in any order. Maybe you have a preferred order that you like to address. I know these are all ones that you've spoken about before, but those are the three that interest me the most. Is there another one that I've left out that, just out of curiosity, that you find the most?
Those are the ones that really, I think, deserve the most thought.
Yeah.
There's a bunch of other objections which are kind of terrible, but
there's a million bad ones. Totally. Right. Yeah.
So chapter 7 of the book is us just trying to clear the path of all what we think are the bad objections. And we start with A, B, C. I think we go up to O.
Well, let's do a fun one, Luke. What's the worst objection? You think? Just to give ourselves a little softball to warm up here, right? Yeah.
Oh, that's a tough one. There are some really bad ones. Oh, there's only one universe. I think that one makes no sense to me. So you say, well, what's the probability of a life permitting universe? Well, look, there's only one universe we know about. It's life permitting, so the probability is 1 out of 1. And so where's your fine tuning? And I mean, if that was what probabilities are, then they're completely useless for science.
That's right.
Right.
That's right.
I mean, if you're trying to test your theory, I've got some theory about any old thing in the universe, right? I mean, about that parrot, which is still there. I can't just say, well, the universe just is what it is. The probabilities are all 1 out of 1. The end. Right? Like the way we test our theories is you got to, you think about whether a theory makes. I mean, probabilities are generated by hypotheses, right? This is right. If you really understand these are predictions. If you really understand your idea about how the universe works, it should take certain possible outcomes and put its bets down about which one it thinks is going to actually happen.
Yes.
And so that hypotheses generate probabilities. You don't just go counting universes. I think that's a pretty awful objection.
Yeah. Agreed. All right. So let's why don't we do the normalization issue first?
Sure.
Maybe you wouldn't mind just giving us the general flavor of this objection and how you like to begin to address it.
So there's two papers that sort of came out about the same time which put forward this objection. One of them was by the McGrews and I want to say Vestrup. I better get that right.
Yeah, Vestrup, I think.
Yeah. And the other one was by, I know Mark Collivan was one of the authors, and I've forgotten the name of the other two. Actually, I can look it up. Just give me a second. The idea is basically, in order to have a probability, one of the things that must be true of probabilities is that the probability of every possibility added up has to equal 1. So this is called the normalization. So that's a rough way of saying it. You can look up exactly what that means. The idea is that if I want to change some of these numbers, if they can vary over large distances, over large ranges, then we're all right. But if they vary over an infinite range and you want to give an equal amount of probability to each possible range, then you can't normalize it. So if I want to say all the outcomes are numbered by, this isn't quite continuous, but natural numbers. So there's all the possibilities are 1, 2, 3, 4, 5, 6, 7, 8, off to infinity. And I want to say, well, they've all got equal probability. Well, the problem is I need all of those to add up to 1. And so the probability of each one times the number of things needs to add up to 1. So if I've got, a 6-sided die, right? Oh, actually, I've got a 12-sided die in here somewhere.
Perfect.
Right, then, and I want equal probabilities. I've got 6. Then each of them gets probability of a 6th. So if I have a 12-sided die, then they each get 1/12. If I have an infinite-sided die, they each get 1 over infinity, which is not a number, or if it is a number, it's 0, and then 0 times, it just doesn't work.
Right.
So that's roughly the objection. Sorry, I've just got the name here. Colivan and Garfield and Priest. Problems with the argument from fine tuning. So that's basically the objection that both sides made.
Yeah.
If you've got these constants, they vary over an infinite range, and you want to give an equal probability to each. They're continuous rather than discrete, but same idea. Then you can't normalize your probabilities, so you haven't got probabilities at all. So
whole thing blows up, right?
That's it. Yeah, you're done. So my responses to that. So I've written a paper on this, by the way, which is called "Fine Tuning in the Context of Bayesian Theory Testing." Which you can go and find. It's a fascinating read.
I will be sure to link it for the interested reader. Yeah.
Excellent. Here's my responses. Firstly, the objection is too strong, far too strong, because the kind of probability that we want to calculate for the fine-tuning argument is of a piece with, basically continuous with, the kind of probabilities we want to calculate in science in general. So if I say I want to take the standard model of particle physics, just the way we think all the stuff works, right? Electrons and all that stuff. And I want to say, what's the probability that I would observe the particular experiment I did with electrons yesterday? Well, if I want to do a prediction, remember, there's a prediction from the theory itself, I have to take into account that there are numbers in that theory that the theory doesn't tell me what they are, like how heavy is an electron. Doesn't tell me that ahead of time. You want to infer that from the data, of course, right? You don't want to put that in ahead of time.
Right.
So if, a possibly infinite range of electron values before you go and look at the data is a problem for a prediction, it's a problem for that prediction as well. So what fine-tuning wants to do is to say, okay, here's the theory. What's the probability of a universe where stuff could stick together to make life? And that's the same sort of calculation, different in detail, but the same kind of thing as saying, what's the probability of that experiment result that I saw yesterday, that the electron, when I shot it at this speed, curved like this through a magnetic field or something like that, whatever. If I can't do one, I can't do the other. And so this objection is way too strong. If it's successful against the fine-tuning argument, it's successful against all the theories of physics. None of them can predict anything.
Yeah.
So it's a kind of.
So if it's a problem for the fine tuner proponent, it's a problem for a lot of other people as well. Right?
Yes. Basically, if we can't handle free parameters that could vary over an infinite range, more than the fine-tuning argument is affected by that, we're all in real big trouble. And so the answer then is to look at, what do physicists actually do to handle this problem? And the answer is, this is not anything new. This didn't, suddenly pop up in the McGrew's paper in 2005 and Colivan's paper in 2005. There's a couple of things that we can do. The first one is, within the standard models, in order for them to be consistent, a lot of the parameters can only vary over a finite range. You can't go outside that range, or the model is simply inconsistent. So that's a sort of an epistemic. That's a constraint problem. So this is the equivalent of Robin Collins building on a response by John Leslie in his book. It's a great universe. So what Leslie has this really nice thought experiment of, you're standing in a fog for some reason. We won't speculate why. but you're standing next to a wall, and you can't see the ends of the wall, but you can see a bit of the wall, and a fairly big bit of the wall. And a single fly comes out of the fog and lands on the wall, on this sort of big space that you're in. And then suddenly, bang, out of the fog, a bullet comes and hits the fly on its one place on the wall and knocks the fly out. And the thing is, if you want to say something like, oh, that bullet must have been aimed. I don't know how they saw the fly through that fog, but they must have some sort of way of doing it. Because, well, if it was shot at random, it could hit anywhere on the wall, but most places on the wall don't have a fly. So it seems like we've got a good probability argument there. And the normalization objection would go something like, well, if the wall is infinitely large, then the probability of hitting any particular part of the wall is 0, or not normalizable, or not calculatable, or it's just a problem either way. So you can't say that it's unlikely that a bullet would hit the fly, and so you can't make any response. And what Leslie and Robin Collins say about this is, well, we're justified in saying, look, I don't know what happens outside the fog, but at least inside the fog, I can try to model my own uncertainty.
Sure.
I can try to work out what's going on there. So that's I think the same applies quite straightforwardly to the physics. There's something called the Planck scale. We don't have to go into the details, but basically, say the mass of the electron, it could be 0 because we know there are particles with 0 mass, like the photon or the particle of light. Negative is a problem. It makes the theory inconsistent. And if it's larger than a certain scale, that's a problem as well. You would need to know how to do something called quantum gravity. You know how to sort out that theory. And so that there is a very clear epistemically illuminated range, as Robin would call it, that we can just get on with. There's clearly something wrong here, and just sort of bringing up a technicality about infinities. We can get on with trying to do our reasoning in the face of uncertainty, and we're not completely, shafted by that problem.
Yeah, good, excellent. Yeah, I'm satisfied with that response. I think that's a good one, Luke. I'm trying to remember because it's been a while since I've looked at, I guess, the literature for this, but Plantinga and Collins take different approaches to this issue, don't they?
I'm not sure about Plantinga.
I think Plantinga rejects. I don't want to get it wrong because I will if I don't have it in front of me. But I felt like Plantinga rejected countable additivity.
Oh yeah. But
it's interesting to see how different thinkers are all kind of, with what you said, like, okay, there's something wrong here, right?
Yeah.
But they might, take a different path on trying to identify what the wrong thing is or what should be given up or something like that. Right.
I mean, there's an open question of maybe we just need a more high-powered probability theory to deal with infinities. I know some people have tried thinking about extensions to numbers in infinitesimals. I think standard probability theory can handle this.
Yeah.
So that would be my objection.
Yeah. Anyway, it's an interesting objection. It's one of those that I suspect probably a number of people who've at least read like the popular level books on this haven't run into, but for whatever reason it's captured my attention. Okay, let's go to one now that does get a lot of attention everywhere, and that's the multiverse. And you've got a lot of interesting things to say on this because it's not like there's just the multiverse. Right. So help us understand what exactly is being proposed as the ultimate. And by the way, when we even went a little too deep, a little too quickly. Generally, when we're looking at the fine tuning data, the theist. Well, I guess it doesn't have to be a theist, right? Because an atheist could say, as atheists have said, yeah, I think fine tuning is evidence for theism. But I actually just think that the problem of evil is greater evidence for atheism or something like that. So there are atheists. I've seen them say, yeah, I think fine tuning is totally evidence for theism, right? But I think people like us, Luke, cards on table, we're theists. We think that this is significant evidence for a theistic hypothesis. But one of the competing hypotheses, often promoted by a naturalist, would be a multiverse hypothesis. So help us understand what this competing hypothesis is and what your current thinking about this would be. Mm-hmm.
Right. So it's the kind of explanation that we're relatively familiar with. So, you see a news report about someone winning the lottery, and you've heard that winning the lottery, the odds of that are 1 in a whatever, 50
Big
million,
number,
50
right?
million
Yeah.
or something.
Mm-hmm.
And you think, okay, something that seems to be extremely unlikely has happened. How did that happen? And the answer in the case of the lottery is we don't immediately think that the lottery is rigged. What we would say is, well, lots of people buy different tickets. So, of course, there's no one's going to write a news story about someone who didn't win the lottery. So what we have is sort of a large sample and then a selection effect. So lots of people buy different tickets. So the probability that there is the correct ticket out there somewhere is not 1 in 50 million. It's much higher than that because lots of people bought different tickets, right? In fact, if 50 million people each bought different tickets, it would be certain that someone wins the lottery.
That's right. Mm-hmm.
And then there's a selection effect. How did the winner end up in the paper? Well, the loser would never end up in the paper, on the news. So there's something that selects the winner out of that sample.
Mm-hmm.
So the idea is, look, okay, it seems unlikely that a universe would get just the right conditions around us to give the preconditions for life or anything interesting happening in the universe. Maybe there are lots of other tickets out there, lots of other universes. They all have to be different tickets. There's no point 50 million people all having the same lottery numbers. That doesn't help. So in some sense, this isn't just more of the universe or extensions of the universe or a really big universe. It's got to be different universes.
Mm-hmm.
They've got to have a different ticket. They've got to have, if I go far enough that way or back in time or in some parallel dimension or whatever, however you want to make your universes, there's got to be different electrons, electrons with different masses and stronger gravity or whatever it is. And then you need a selection effect. How do we pull the winner out of the draw? Well, there's no one around in all the losing universes with their losing ticket to ask, well, I wonder why this universe doesn't have the right properties. There's no one there. Mm-hmm. It's only in a universe which has the seemingly freakishly unlikely conditions for life where anyone is like us sitting around going, I wonder what the heck happened around here. That's the multiverse explanation of how our universe came to be life permitting, even though it seems very unlikely that it would. That a sort of randomly chosen collection, a universe with randomly chosen or indifferently chosen constants would. It's important to realize it's not really the multiverse. I mean, if it exists, then there's the multiverse. But within physics, a multiverse theory is sort of a type of theory. A type of idea. I said before, exactly where is this other universe that has this different value of the electron mass? How heavy is electron? I mean, in some multiverse theories, it's just kind of, just go that way far enough and it'll be out there, bazillion, squillion light years. In some, it might be before our universe, so the universe just sort of bounces along, expands, contracts, and starts again, and then scrambles its constants every time. And eventually, here we are. They might be completely disconnected to our universe. They really exist, but there's no way there from here. There could be the sort of pictures. I guess this would be an example of the first one, but sort of bubbled universes within a bigger universe. There's the multiverse, a real proper multiverse theory. Is not just the general point that, maybe things are different. You've actually got to start now telling me, give me as a physicist something I can use. So that's roughly, give me a theory that can predict some stuff and tell me where these universes are and how many of each type there are and such things. So that's the multiverse idea, roughly.
Yeah. Yeah, good. So I guess I mean maybe it's just like just an easy way around it, and that would be like, well, look, I already have reasons to think that this theistic hypothesis is true. Maybe I've contemplated the contingency argument and formed this grand theory of everything, right? And so this seems to be confirmatory of that, and maybe I don't really have any independent reason to think the multiverse theory is true. Or do we, Luke? Are there some other very strong considerations in favor of the multiverse aside from just trying to stalemate fine-tuning data that you can think of?
So, I mean, if you think fine tuning is a problem to be solved, then the fact that the multiverse, if it was true, would explain it. That's a reason. I think this is correct. I think that it is a reason to think that there is a multiverse. Not everyone agrees with this, by the way. I'm having constant discussions with, occasional discussion with Philip Goff and a number of other philosophers around the place who don't think even if it isn't. Sorry, fine-tuning is not evidence for the multiverse, but I disagree. I think it is.
Yeah, how could it not be? It would have to be, right? Just like I think it could be evidence for a number of other things as well.
I don't want to. There's a couple of papers on this that I still don't understand, so I don't really want to present this objection because I don't get it. But very roughly, it's supposed to go something like, yeah, it would explain why there's a life-permitting universe out there somewhere, but it wouldn't explain why this universe is life-permitting. And that doesn't make any sense to me.
I guess one of the other, well, I was going to turn and ask you other objections you have against the multiverse, but some people accuse proponents of that theory of committing the inverse gambler fallacy. And I think that's an interesting consideration. Yeah. But the first thing I wanted to focus on was just whether there is other reasons for wanting to hold to a theory of the multiverse, because I think there are other good, like not just any old reason, but like pretty plausible good reasons, right? Which I think most theists would want to say, yeah, we've got those for the whole theistic hypothesis thing. So this is just sort of another weight in the scale, right? And we can look to those other considerations to kind of break the stalemate, if you will. But that will only work if there aren't other weights on the other plate in the scale, right? Mm-hmm.
I think the best that is out there is a sort of it's very circumstantial, but the reasoning goes like this: there are some properties of our universe which you could just put in as what we call in physics initial conditions. Whenever you try to explain something in the universe, you need to know how it started and how it changes. Mm-hmm. So how it changes is the laws of nature. They take the form of how something changes with time relative to everything else. So if you know any physics at all, you might know F equals ma, Newton's second law. I should know that. Force equals mass times acceleration. What that's telling you, acceleration is it's not telling you where things are. It's not even saying how fast they're moving. It's saying how their speed is changing. Well, their velocity is changing, really. So this is what the form that the laws of nature have, even quantum laws and gravitational laws and GR and all that sort of stuff, general relativity. So you need to know how things started and how they change. So there's various things about the way we think our universe started, which seem to be, I guess, how would you say this? To be explainable. So the question is, if I go backwards in time, so here's, I go backwards in time, and I say, here's my initial conditions of the universe, and then if this is what happened then, and the laws are what we think they are, the universe today is roughly as we would expect, and that's when you think you're on the right track. The question is, did I put this point here too late in the universe? Is there a story before that point?
Sure.
That might explain more. One of the sort of like writing a prequel for the universe, right? One of these prequel theories is called cosmic inflation. And the idea is that the universe expands, but before the expansion starts, there's a very, very rapid exponential blowing up expansion, not just a usual sort of boring, slow expansion, but a sort of doubling and redoubling of the size of the universe. If that were true, it would explain some stuff about our universe and why it looks the way it looks, just the sort of way things are laid out. here's the argument for the multiverse. When we try to think of some physical stuff to put in the universe that would make it expand in that particular way very early on, the ideas that make that happen very often lead to, we're told, a multiverse where you don't just get one universe expanding, you get lots of little bubble universes expanding. Now, you on top of that need to sort of shoehorn in a explanation for why, say, the mass of the electron is different in all those universes. There's some hand waving there. I don't see a lot of detail in these models, but that's I think the best that case can be. It's circumstantial on top of circumstantial that this theory would explain the way our universe is, and a theory that explains how that happened seems to imply a multiverse. That's about, yeah. I mean, it says sort of, it's almost hearsay.
Sure.
6 degrees of separation. But that's the argument that's put out there. Basically, cosmic inflation implies that there probably is a multiverse.
Okay. And I sort of got a flavor of, I guess, your impression of that. Is there anything else you want to say about it, or?
It's hard to appraise. I mean, the history of science has shown we're not very good at working out the way the universe works without data, and it's trying to do an awful lot without data.
Sure.
But that's the argument.
Yeah. Okay. Well, let's turn now, because you've got other things to say about the multiverse theory. So where's your thinking at on this now? Because I take it that you don't think that it is an equally good explanation of fine tuning. Clearly, you're on opposing sides of your co-author there, right? So what breaks it for you? Mm-hmm.
I've come to think that I think it's actually irrelevant. I don't have to argue that it's false or probably false or wouldn't be. I think it's irrelevant. Here's the reasoning.
Sure.
The question we're trying to answer is, is there something like the bullet coming out of the fog and hitting the fly? Seems like there's something to explain there. And it didn't just hit some random bit of a wall. It hit something. One of the ways you might cash out that there's something to explain here is you see a way it could be explained. Oh, if there's someone with, an infrared, someone who hates flies and is a good shot and has an infrared scope or something, I don't know.
The Predator, yeah, right.
Yeah. That would explain it better than chance. So the question we're trying to ask is, this universe, there's some bits of it that seem amazingly well put together. Like, the animal kingdom and the cells in every body of every animal, and we're trying to work out, is there anything like that? What happens to that when we look down deep into physics? And fine tuning says, well, look, the way the constants of this universe are put together are pretty amazing as well. So that impression of this didn't just happen follows us from the sort of biological realm all the way down to physics as we know it, the standard models. You don't just get this stuff for free. And the question is, what do we do with that? And what the multiverse says is, look, maybe there's a deeper level that explains those constants. And the point is not whether that's true or false. The point is, well, what I want to know is not whether one level explains the level above it. That wasn't the issue. Physics explains chemistry. Chemistry explains biochemistry. Biochemistry. We can allow that all to work beautifully. The question is, what happened to that impression of this place is well put together? And so what we would want to know is, okay, whatever physics is really at the bottom, is it well put together? Do I get that same impression? Is it the sort of thing where we'd say, okay, that doesn't just happen by accident? So if a multiverse really is the way we end up with a life-permitting universe, do I get a multiverse for free? One way to think about this is just by putting it up a level. So you might think that our planet relative to the sun is in just the right place, that it could have been closer and too hot, or further away and too cold, but it's in just the right place relative to the sun. And the question then is that something, remarkable? And the answer might be, well, we live in a big universe and there's lots of planets out there. And so one of them would have to be somewhere, in the right place relative to its sun. So there's nothing particularly interesting going on here. And even if that's true, it's the question, keep your curiosity on. Don't bail out on this question too early.
Mm-hmm.
The question to ask then is, okay, a universe with lots of planets, is that the sort of thing that just happens? And then you go down to the cosmology and galaxy formation and fine tuning, and you say, oh no, right?
Mm-hmm.
If you want lots of planets to explain that higher up level of how the Earth got things just right,
Mm-hmm.
if you want lots of planets, you got to get your universe right.
Mm-hmm.
And now they say, well, lots of universes. Well, do we have to get the physics just right to get the multiverse to work, to get lots of universes to work so that our universe comes out somewhere? Is that the sort of thing we get for free? And
Mm-hmm.
the impression is given that, just any old thing happens. But the problem is we don't actually know, because we don't have a standard model of the multiverse to ask these questions of.
Right. Mm-hmm.
If we just went, planets, maybe there's lots of planets out there, we wouldn't be able to answer the question of, okay, is it easy to get lots of planets in a universe, or is that a hard thing?
Mm-hmm.
Right? It's only when we have the deeper physics of the standard model of cosmology and particle physics, we can go, oh, no, right, you've got to get a lot of stuff right if you want lots of planets. And so now we say lots of universes. Well, is it lots of universes? Is that the sort of thing you get easily and naturally for free, or have you got to do some interesting stuff in the real deep physics of the universe?
Mm-hmm.
And we don't know. And so I think the conclusion of this is that the multiverse is just irrelevant to the question we're trying to ask. It might be the explanation of fine tuning, but what we want to know is it itself just another example of this? This place looks well put together. So I think it's irrelevant. I think that until we've got a standard look, if a standard model of the multiverse comes along tomorrow, right, then we can do what we do with the standard model of the stuff of our universe, particle physics and cosmology, which is take its fundamental parameters and change them and see what happens. Until we've got that, we just don't know. And so the best handle we have on is the fundamental stuff of reality, of physical reality, just any old stuff, or is it remarkably rare, significant stuff? The best handle we have on that is still the standard model of particle physics. So that's my thinking on this. It's just, it's just giving up, I guess. It's not trying to answer the question as much as it is saying, maybe that in the future we'll know a bit more and a different answer will come out. Well, let the future come. At the moment, we'll do the best we can with the information we have.
Yeah, that's interesting. That's so a couple things I want to explore with that line of thought there. So I'm trying to think like what could make the multiverse relevant, and from a physics perspective, I don't know, because I don't play that game. But some things might seem initially promising but are problematic. So there's the one of like, well, maybe it just shoots out all possibilities, right? But we know that leads to contradictions, right? There's the possibility that there's just this universe and nothing else that excludes other possibilities, right? So that can't be right. So we have to have some sort of constraints, right? And then we start to put these constraints in, and then what? Just think about this in the abstract. Well, then it just seems like, okay, I don't know how many constraints those are to avoid the contradictory implications and stuff like that. But it seems like whatever they are, there's probably far more ways that things could go wrong, right? Even in a life-permitting universe that I don't typically see if the multiverse hypothesis is true. Right? Like the laws of physics are what they are until Pat is 33 years old and then they radically change or something like that. You know what I mean? You see what I mean, right?
Yeah.
Or until I was 17, until I was 19, right? Like those all seem like possibilities that might not lead to immediate contradictions or stuff like that. That that, like, if that was the case, like if I don't know, the electron changed its weight, and I guess depending on whether you're an essentialist or not, if that can even happen, right? Things would have gone pretty bad for me probably when I was like 17 or something like that, right? So and then there's the whole issue of Boltzmann brains and brief brains and all that stuff, right?
Yeah.
So what I'm kind of putting out there is like, okay, given that we don't have this standard model of the multiverse, like, can we still start to make certain predictions with some constraints? And where do we wind up if we do? And is that enough to begin to maybe tip the scales one way or another? You see what I'm trying to get at here, Luke? Yeah.
Yeah. So I think it's important that the multiverse, you can't just say, oh, any old thing happens. Certainly not if you're trying to, if you think you're doing physics when you're doing the multiverse. If you're just doing sort of, metaphysics or whatever, then feel free. But if a lot of this objection comes from people who think it's a physics idea, which it can be, but if you're doing that, you've got a lot. It's got a lot of work to do. It really has to explain some stuff. It's supposed to. I should be able to take your multiverse idea. So someone publishes a multiverse theory, right? And it's a specific thing, right? It's not just any old stuff. There's really, like, how is the universe laid out, and what are the sort of distributions of all these other universes and stuff. I should be able to take that idea and, at least in principle, do what I do as a physicist with it, which is make some predictions. Yeah. If that multiverse was the reality that we are in, what is the probability that I would observe the electron that I actually observe? Now, it can't be one of those electron values on which life is impossible, but there's a whole bunch of electron values in which it is possible. It's not a wide range, it's a narrow range, but there's still something going on there. And so this Boltzmann brain idea, which you mention, is just, look, the way that our universe made life, and the life that we understand here, it has a sort of consistent history to it. Right? We all remember yesterday, and there's evidence of the history of the world and the solar system around us. But you could make this, or a brain that had thoughts, just sort of by particles randomly coming together. And that seems unlikely. But the problem is, if you've just let any old thing happen, you've got to worry about what's more likely, this sort of universe, or the brain randomly coming together out of chaos sort of scenario. What if there's a brain having thoughts about a universe, is it more likely to be this kind of brain, which is actually in a universe, or just that randomly assembled brain? And that's a question that your theory's got to be able to answer. And the question is that, what sort of constraint does that put on your multiverse theories? Is that kind of just a technicality, and don't worry about that, if that turns out to be the case, we'll just throw that theory away and get a better theory? Or is that the sort of problem that seems to affect most multiverse ideas? And given that it's if you're trying to sort of do stuff by random, just sort of make a whole bunch of universes and let our universe come out, accidentally making too many fake brains in universes, it could be, and I think plausibly is, a very generic problem with the multiverse, in which case you've got some fine-tuning to do of your multiverse,
right? Yeah,
to make sure that it actually explains our universe at all. And this is the whole, what happens down at that bottom level? Do I have to turn some dials to get just the right stuff happening in the multiverse? We don't know, because we don't have a theory.
Yeah, and so your response here, I like it, because it's very nuanced. You can tell that's because you're somebody who really understands this debate. Is sometimes you hear on the popular level, like, oh, well, the multiverse itself has to be fine-tuned. And that's a little too quick, right? Because, like you're saying, in a lot of cases, we just don't know, because we don't have a lot of these things worked out. But here's some things that we might have to worry about.
Yeah.
Brains, popping out of chaos, right? And it seems like these might be wide enough issues that, you might need to start fine-tuning on that lower level. And you might have this sort of general relocation where a But until we get some, some things really worked out in detail, we just don't know. Is that a fair way to describe it? Mm-hmm.
Yeah, and so it shouldn't affect, our appraisal of, we're just trying to do the best with the evidence we have.
Mm-hmm.
The fact that we can almost imagine a scenario in which the universe turns out to be, not amazingly well put together at its fundamental level. Well, I can imagine some scenarios where it is. So, what do we do now? It's just the people who don't want to see design in nature can imagine a scenario where it might turn out that there isn't, and that's it. That's kind of what the multiverse is. It's we don't have a theory that actually does the work that a multiverse theory is supposed to do at all, really.
Yeah. Mm-hmm. Now, do you think that that just stopping it there, though, does that still neutralize it for both sides of the debate, though? Or do you think that coming from the design hypothesis, you can still push this through? Or does it just wind up that everybody's just in this, I don't know, so fine-tuning isn't really doing much for us?
No, because I think that if there's on any understanding of God that anyone believed in before, or the most believed in before, the fine-tuning evidence came along, it's a life-emitting universe is more likely on a designer hypothesis.
Mm-hmm.
Remember what they're trying to show. I think the design intuition is so strong. Like, this place looks pretty well put together.
Mm-hmm.
Finding it all the way down to the bottom of the universe says that, right? So, if you're amazed by a hummingbird, then you should be amazed by the universe, and nothing has changed there. So it's really making the point that the argument from design has not been touched by science.
Yes, I see. Yeah. Okay. Mm-hmm.
Mm-hmm. And so what they're trying to say is maybe there's a lower level of physics where things don't look amazing.
Mm-hmm.
Well, maybe, maybe not. I don't. The best we have is the best theories we have at the moment, the standard models, which are fine-tuned.
Yeah. So there's no scientific reason to give that intuition up, that seeming, right?
Yeah, exactly.
Yeah. Yeah. Mm-hmm. Yeah. Good. I like that. That's a good way to approach it. Okay. I know we started a little bit late, bumping up against our time here. So real quick, Luke, I'd love to the third one I wanted to touch on was the necessity objection. This is kind of an interesting one. Like, hey, it's the way it had to be, right? I couldn't have been otherwise, right? And we don't, we can't just spit out other universes, right? And yes, I know you've got your fancy models that you do, and they seem consistent, but why think that that's a real possibility, Luke? Sorry, present it however you think is the most interesting way to present
I think
the
that's
necessity objection. Right?
Yeah. Mm-hmm. I mean, suppose there was I made some model of the universe, which is, a mathematical. I should be able. The idea of a mathematical model in physics is, I should be able, whatever mathematical construct I need, where I can ask the same question of my model that I can ask of reality, and see whether they agree with each other.
Mm-hmm.
So you can think of a model of a house. So if I want to know whether some couch is going to fit into my living room, in reality, if I have an accurate model of my house, I could get an accurate model of the new couch and just see whether the model couch fits in the model living room, right? And so the idea of a mathematical model is, I should be able to ask the same question of the model that I ask of the universe, and then we can see whether they match each other. What if I did this experiment? What if I, threw this electron through this magnetic field and whatever? So within that, sometimes we have what are called free parameters, where the model doesn't specify a certain number, and so that part of nature is not predicted. You just go and measure it, and then on the basis of that, you go do more stuff. So, for example, I think there are things called electrons out there. They're very light. They have a negative electric charge, but I don't actually know what their masses are. So the model, which is true of the standard model, doesn't predict their mass. But I could go and measure their mass, and then on the basis of that, I can predict all sorts of stuff. I mean, what electrons do in chemical bonding and yada, yada, yada. Suppose there was some number out there that I thought was a free parameter, and then as I start to measure it in appropriate dimensionless form, the digits of the number start turning out to be 3.1, and I keep measuring 4, 1, 5, 9, and I go, oh, hang on a minute, this looks like pi, right? And we might think that, some deeper model is going to come along and explain why what I thought was just some any old number that I have to go and measure is actually a deep mathematical constant, something that could not have been different.
Sure.
Right? So if I draw a bunch of circles and look at the ratio of their diameter to their circumference, I can measure that a whole lot. And I keep coming up with this same number, the ratio of the two. Anyway, so the necessities objection is like that. When we really know what's happening under the scenes, we'll realize that these numbers aren't easy, like pi or 2 or something, but there'll be some reason why they are exactly what they are, and they could not possibly have been different. And so if you're a physicist giving this objection, you think that deeper thing is going to be some deeper theory of physics, some uber theory, some grand unified theory of everything or whatever. And if there are some philosophers who don't even need that much detail. They're quite happy with these numbers just being, they just are what they are, and that's it. And they had to be what they are.
Whatever the constant values happen to be, they are necessary.
So it's not it's not supposed to be a brute fact explanation. Actually, I'm a bit fuzzy on this point, exactly what people mean by this. But it's not supposed to be, I just said they are what they are.
Yeah, some philosophers think that if you just kind of call something necessary, it's magically explained. I super disagree with that.
Yeah.
Right.
So Oppie, I've heard speak along these lines, Graham Oppie, and I just don't get it. So he seems to say, look, let's consider the hypothesis that the way the universe is necessary. It just had to be this way, and there's nothing else to be said about it. And how do we know that? Well, that's our hypothesis, and we see what that explains about the universe around us. And one of the things it explains is why the universe is life permitting, and the answer is because it had to be. It had to be this way. It couldn't have been any other way. And so it sort of that theory wins by a priori announcing. Maybe I shouldn't use words like a priori.
Yeah,
by simply announcing that all the probabilities are 1.
Yeah.
So I win.
So I have an immediate reservation with that. Aside from the fact that I think things can, even if something was necessary, it doesn't mean that we're done with seeking explanation. I mean, there's many things that we can, necessary truths that have deeper explanations in mathematics, for example, right? So just even if something is necessary, it doesn't mean that like that's it. We're done explaining things, right? So that's one thing to consider. The second thing is this, right? Just saying that whatever the constant values happen to be, they are necessary, doesn't predict that we'll have the constant values that we actually do, right? You need to specify that. And if you specify that in your theory, like, so whatever the constant values have to be, they're necessary. That's a general statement, right? So if you want to just make it like you have to specify it upset, but then I don't know how complicated that is, but I'm assuming from a physics perspective, that's a pretty complicated theory if you make all those specifications right out of the gate. Okay, fine. Then I'll just say, well, theism's a lot simpler of a theory at that point, right? So it seems like that'd be a classic case of borrowing from the priors if you're going to make those specifications.
I think so, but you run into this issue of what probabilities are. So if you're going to say the sort of things that you've just said, and I think those are correct, but you need an idea of probabilities, which is not just sort of objective chances, not just actual ways the universe could have been different, or hypothetical frequencies or anything like that. Because Oppie's going to reply, where are these probabilities coming from? The universe couldn't have been different. So what you want? They have to be epistemic.
They
have to be, and you need a robust theory of that. Now, I think we've got that, but I think that's going to be the sticking point. In fact, I'm convinced I mustn't understand his idea properly, Oppie's idea, just because it's so. It seems to me that if this maneuver, if it's possible to do this on fine tuning, I could do it anywhere in my scientific work. If someone says your theory is disproved by this data, it says that it's very unlikely. So I've got a theory that this coin, this imaginary coin, is fair, and that it's not weighted one side or another, and I flip it a large number of times, either side could come up. And then I flip the coin 50 times in a row and they all come up heads, 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 heads. And it seems like what you should do in that scenario is to say the coin, the hypothesis is very unlikely. Not disproved, that's too strong. We don't do disproved, but strongly disconfirmed. It's very unlikely that a fair coin goes heads 50 times in a row. And it seems like there's a maneuver here where you say, oh, no, it's necessary that this coin turns up 50 times. It always turns up heads. And that's just a necessary fact. And I don't understand. Clearly, Oppie would not say, no, you can't do that, right? Otherwise, science is done, right? We can't conclude anything from anything. But if I can't make the maneuver there, why can't I make it with the constants at the start of the universe and say, oh, whatever they, I don't even know how to say it properly. I was going to say whatever they are, they're necessary. I think Oppie says that a lot more carefully, but that's the sort of the reason behind it. The one of the objections to this that worries me as a physicist is if there's a necessary, if it's necessary that the electron has exactly this mass, it seems like there should be a reason why it has this mass. I mean, there's a necessary reason why the ratio of the circumference of a circle to its diameter is exactly pi, and it's 3.141, and we can do all the maths behind that.
Right.
So if I know the whole scenario, if I know that deeper reason, I can actually derive the number. Well, should I be able to think hard enough and derive the electron mass? Is that a consequence of this idea? And I'm not entirely clear on that. But if it is, then this is kind of the ultimate win for armchair physics. We didn't have to look at the universe at all. If we were smart enough, we could stay in Plato's cave and just look at the shadows and work out how the whole of reality works. I'm so confused about this idea. I'm convinced I must not understand it properly.
Well, it's a very modest position to take. I think there's several issues with the necessity objection in general, but if people want to explore that further, I will direct them to the recent conversation I had with Dr. Brian Cutter on the conversation we had on psychophysical harmony. We went a little bit deeper in that, but this has been very good. Now, I'm sorry, did you want to add anything else, Luke?
No.
Okay. Good. Okay, so we've covered a good amount of territory, and hopefully we've explored some depth that doesn't often get covered on podcasts around this topic. Anything that we left out that you're itching to mention, or are you satisfied with the product that we've created today, Dr. Barnes?
That's a good set of things to think about. Well, I should say I'm giving a talk in a couple of weeks about God and randomness. I've been actually thinking about that sort of aspect of things. That this idea of design in the universe is often set in opposition to chance.
Right.
And I think we need to very carefully tease apart exactly what chance means, because there's an awful lot of meanings, the way we use the word chance, the way it's used in science, where there is no opposition between design and chance in those restricted senses. And so that's what I'm trying to think through at the moment. Hopefully I'll think through it enough in time for this talk.
Have you seen Dr. Coons has a nice little article on reconciling meticulous divine providence with objective chance. I don't know if you've seen that one.
I'm going to go Rob Coons. Yep.
Yeah. I can send that, and I'll link it for anybody else who's interested in checking that out. But in the meantime, this has been great, Luke. I'd love to have you on again, but please give all the relevant plugs. Obviously, this book, I want to encourage people to pick it up. A Fortunate Universe. It is a really good, and it's a fun read. It not only has great depth, taught me a ton, but it's fun. You have great humor. I always love when otherwise technical stuff has a good healthy dose of humor in it, which you do throughout this book. So I definitely want to encourage people to grab this, but please mention anything else.
So Geraint and I also wrote The Cosmic Revolutionary's Handbook, How to Beat the Big Bang, which is God doesn't get a mention in this one. It's just about cosmology. But we kept getting, this is I think it's a universal thing. Whatever job you do, people try to tell you how to do your job. And this is everyone gets this. So as a cosmologist, people try to tell us how to do our job. We get emails like, "Here's my theory of the universe. and the the standard emails. The phrases you're looking for are, but I just can't do the maths. Retired engineer. Anyway, so we thought, look, here's how to overthrow the Big Bang Theory if you really want to do that.
That's
we think
cool.
It's a good idea.
I have not read that one. I'm going to pick that up. I'm looking forward to that.
Yeah. It's just, here's the data it actually explains, because very often in these emails they explain one thing and they forget that, you know, there's the rest of science out there, at least of cosmology out there. So that's, again, supposed to be a bit of fun. Like, you know, the opening quote is, to get behind someone, to stab someone in the back, you must first get behind them. And so the idea of, you've got to learn what these theories are before you can overthrow them. So if you really want to, there's you know, if you want to learn about the Big Bang, it's great for that as well. But it's pitched as, if you want to overthrow this terrible idea, then the first you've got to do is learn about what it actually is, what it actually does, if you then want to storm the castle.
Awesome. Well, I will link those two books in the show notes. And Luke, a website or social media presence or anything you want to mention on that front?
Oh, I'm around the place. You can just
Right.
find me. If you buy the books, that'll be fine.
Great. I will put those links in. Dr. Barnes, thank you so much for being here. And gentle listeners, please like, share, comment, and subscribe. We'll see you next time.